Good afternoon, everyone. I'm Thomas Anthony. I'm from the University of Alabama at Birmingham. We're a big medical research university in the South. And mainly what I'm going to be talking to you guys today is about how we accelerate our medical research using our high-performance computing cluster. One of our shining examples is how we've accelerated Parkinson's disease research itself. So I'm a computational scientist who works with UAB IT Research Computing. We build out our HPC platform. I'm also the director of the Big Data Lab in the School of Engineering. So this is an interesting problem. So our neurologist comes to us and he says, well, I have a problem. I have a workflow. It takes a lot of time. I've been running it on my local machine, which is fairly beefy, has a lot of storage. I'm currently working on 40 images, but it takes about a week to run that workflow. And you can imagine at 40 images, and that's a decent sized data set. In the medical community, if you have about 10 or 15 subjects, that's supposed to be a big data set. And he was looking at a year's worth of processing, at least with that. Wanted to improve the process itself, as well as scale up, because let's face it, we are living in the era of big data, and he wanted to see how much he could do it with. He went out, and so he said the problem, one is, can I build a biomarker to diagnose Parkinson's disease accurately? Can I do it using imaging, mainly MRI imaging? Because MRI is cheap. Everyone gets an MRI scan of the brain. Every corner in a big city has an MRI scanner. And using that, can we build out a good classifier where we can predict our Parkinson's disease itself? Now, MRIs are a good and interesting imaging modality because there are a lot of MRIs that are collected in America every year. And so if you do image processing, you know what a pixel is, right? So that is the dot that you see on your screen for an image. Now, this is a three-dimensional image of your brain, so you're looking at a volumetric pixel or a voxel. So in an MRI image, we're looking at between 6 and 12 million of these volumetric pixels. They have a lot of information in them. And that made it a really good target, because right now when you get an MRI scan, you look at the radiologist's report, which is about half a page that says, okay, I see a lesion here, maybe I see some other things, I see a stroke that has occurred here. But there is still information in that scan which could be used. And that's what we are using. So this is part of my bigger talk, which is known as data on the table. Basically, we are leaving that data, that information on the table. So this is standard MRI scanner. And we know that in the last 20 years, MRI has revolutionized the way we do medical imaging itself. So how can we get from those usually grayscale pixels to an image? Now, this is going to be highly unstructured data. I cannot put it into a database. I cannot say, okay, this is this part of the brain. So this is a very classical big data problem itself. And in order to use it, we need to have a good amount of computing behind it. So why is this a big data and HPC problem? So I hope everyone is aware of the 4 V's of big data. That is the volume, velocity, variety, and the veracity. So this hits all of that because there is a lot of volume of the data that is coming out, the velocity, depending on how many scans are going on. There are variety. In MRI itself, there are multiple modalities. You can get the structural, the functional imaging, and then there is a lot of uncertainty of the data. That hits the veracity part of the data itself. So what we started out with, or what the researchers started out with, was the straight-up imaging approach, whereby the physician says, okay, I see this is a subject, this is a patient. I send them to the scanner. The data comes back, and we do some of our modeling using a high-performance, high-throughput computing, and then we do analytics, and hopefully we have a pipeline going back to the physician. Now, the top part of that pipeline we have completely automated. So as of today, once a physician requests for the scan is gotten, we can directly pull out from the scanner into our HPC infrastructure and storage the scans themselves. So we do that using something known as XNAT. And if you're interested in that, Ravi is here, he can talk to you more about that. Then we go into our modeling with our HPC and HTC systems. And we get all of that information, how we model the brain, and then we run the statistics on that information itself. So let me show you the first workload. This is basically a very simple one. This is what the researcher came to us with, but it was taking him weeks to do just a simple data set. What we initially did was move it on to a much more, we distributed his problem where we could, we parallelized his problem. When we ran out of capacity on our local supercomputer, we went to Oak Ridge, and Oak Ridge helped us. Exceed gave us allocations to run some of those computations itself. And then Oak Ridge domain scientists actually helped us parallelize a lot of that code because they were SMP bound and they helped us parallelize it well. So you can imagine how a researcher who was very bound by what he could do in a few years could get to using that high performance compute fabric. And this is some of the results that we have looked at. So as our generations kept going, the classification, so the red dots that you see, that is like the best classifier that you can get on those images themselves. And we were getting really good prediction of unknowns. So basically using a very cheap $300 MRI scan, which your insurance pays for, we could build out a classifier whether you have Parkinson's or not. Compare that to the regular test for Parkinson's is a DAT scan, which is very expensive, involves putting a dye in your brain. A radioactive dye in your brain is only available in 22 states in the United States. So we built that out of MRI images. So this is a small little video that I'm going to play on, let's see if I can play that video. Oops. Let's see. So that is how quick, that was our speed up. So we brought down that researcher's computing time from 342 days to less than 3 days processing. And in order for it to be useful in a clinical context, that is the speed that you need. And if you look at the final point here, by the spring of this year, we've now integrated GPUs as well in that. We are looking at within half a day. So by the time the scan is taken and goes to the radiologist or the neurologist for a read, we should have a helper. We're not saying we're diagnosing it, but it's a helper, it's an educational tool saying, hey, this is a chance of you being having Parkinson's. And then now we've improved that workflow. So that was just imaging. Now we take doctor's notes, we take demographic information and pull all of that into that model in order to build a better classifier for what we've been doing. Now we've also applied the same for other diseases, Alzheimer's, schizophrenia. In fact, we got the highest score out in NIH R01 last week. We got a score of 10 based on this. We've done this for cancer screening, and I actually used the same exact algorithm to detect weapons for a DHS project for the Department of Homeland Security. When you are screened at the airport, we use exactly the same. If we can detect those tumors, we can detect those weapons as well, because it's again a three-dimensional scan. So we've been using these techniques, and these are our partners. We work a lot with our vendors. DDN is one of our primary vendors. We have about 6 petabytes of storage with DDN, with GPFS, which is directly connected to our high-performance computing system. And our data sets are huge. That the graph time that you saw for analysis was on a 44 terabyte data set. So analyzing that fairly quickly becomes a bottleneck, but we actually have the exact same, the 14KX or the 12KX that's back there. We have pretty much the same one that DDN is showcasing out here. And we work with our other partners as well. We've also gone into GPU computing. And of course, we have our funders, like Michael J. Fox is one of our big funders. The NIH, the NSF, and also we got a big storage grant from the Alabama Department of Commerce. So if you have any questions, I can hang out for a bit. And I think I finished it right on time. So thank you.
I agree. I think you're perfect. Thank you so much. We definitely appreciate having our guest speakers here. Thank you, Thomas. Did anyone have any questions for him? Any questions?
Any?
Well, I love the research you're doing, so I definitely appreciate that.
So what our next plan is, so right now, in order for it to be clinically relevant, we need to have that return pipeline as well. So we're actually talking to folks at the Icahn School of Medicine, because they have a good clinical return pipeline in order so that the physician can see, okay, so maybe this medication is working, this one isn't. Maybe we need to control it with some other way. And so we've been working on that pipeline as well. Right now, our forward pipeline is working from the scanner till our modeling, but we're working on the return pipeline as well.